All right, hello, welcome to lecture number 4 on, or 5 is it? I forget, on RF filters. So I think, am I still sharing my screen here? Somebody can answer.
Yep.
Okay, great.
That's lecture 5.
Lecture 5 it is. So first I'll give some comments on assignment 3. Not everybody finished it, and I think there's some clarifications I can make. And then we'll start going into all the filter goodness. So we'll see how filters are integrated in RF systems and some basic filter construction, why we don't use RC filters and active filters. And finally, when we get to the LC filters, which are the types we're going to use. And then we'll have a little demo on how to design and simulate a filter. And lastly, we'll have our next assignment, assignment 4. All right, so on assignment 3, a question a lot of people had was the transformer for the IF and RF. If you calculate the inductance that it should be, it ends up coming to something around like 80 microhenries or somewhere around there. And so previously I'd said that the limit for inductances was 15 microhenries. That specifically was for high Q inductors, which are used in things like filters and LC tanks for oscillators. But for transformers, you can usually get much higher inductances because the Q is not as important. So 80 microhenries is a reasonable value. But much higher than that is not so reasonable. Okay, the other thing is the definition of conversion loss is defined between 2 different frequencies at 2 different ports. So the whole point of the mixer is that you're converting between frequencies, and the conversion loss is defining essentially the performance of that conversion between frequencies. However, isolation is defined between the same frequencies at 2 different ports. So like LO isolation, in the case of our up converter, was defined between the levels of 28 megahertz at the LO port versus the RF port. So they're a little different. Also, if you're getting 50 dB conversion loss, you got a problem with your mixer or the way you're measuring the conversion loss, because 50 dB is pretty terrible. You should be getting roughly somewhere in the neighborhood of 15 to 10 dB of conversion loss. What's next? Right, so the oscillator everybody designed used a common collector configuration for the amplifier part. And although a common collector amplifier is usually used as a buffer, when you use it in an oscillator, it doesn't quite work that way. So there's a thing called load pooling, where if you have an oscillator and you attach a load to it, what'll happen is that that load, depending on its exact magnitude and phase, that load will cause the frequency of oscillation to shift as well as the amplitude of oscillation, even if you have a common collector amplifier as part of your oscillator. So you do need an additional transistor to act as a buffer between the oscillator and the mixer. And also, if you follow the guidelines listed on the assignment regarding the buffer amplifier, then things should work out. So if it's not working out, you should take a look at the way you designed your buffer. You might want to simulate it in isolation from the rest of the circuit. All right, so on to the filters, unless people have questions. If you do, speak up.
I had a quick question on the conversion loss.
Yes.
In the assignment, you specified that we're measuring it, or for example, when going from IF to RF, it was, we looked at the difference frequency in RF, not the sum frequency. Is there a reason that that's chosen to?
Right, so in the case of the mixer you designed for that assignment, it's supposed to be acting as an up converter. And so we were converting up from 1 megahertz to 27 megahertz. And so the LO is 28 megahertz. So the difference is 27 megahertz, the sum frequency is 29 megahertz. And because the 29 megahertz is not, it's not the frequency of interest, 27 is. So conversion loss is defined between the frequency that we want and the input frequency.
Oh, gotcha. Right.
Right. Anything else? No. Okay. So on to filters in RF systems. So as we've mentioned many times before, down conversion and up conversion are pretty common operations in RF systems, and to do so we use mixers. And as I just mentioned, the output of the mixer gives you the sum and difference frequency, and usually we're only interested in one of them. So how do we get rid of the other? And to do that we use a filter, of course. So in the case of our up converter, there's essentially 3 frequencies that are very close by that we need to take into account. So we have the 27 megahertz signal of interest. We have the 29 megahertz, which is the sum frequency. And we have the 28 megahertz, which is the LO leakage from the LO port to the output. And because LO isolation is not perfect, we're going to get some LO in the output. So we need to be able to filter out 27 megahertz from the 28 and the 29. And to do that, we could use a bandpass filter, and we'll see that shortly. So the other thing is, I mentioned this in the mixer lecture, but there's this problem with mixers called the image frequency. So let me get my little pointer out here. Or where is it? Here it is. Okay, so I showed this diagram last time, but I want to reiterate the point because it's kind of important. So the blue line here is representing the LO frequency. In this case, it's 28 megahertz. And this is for a down converter, by the way, not an up converter. So we're going from a high frequency to a lower frequency. So the RF signal here in blue is the signal that we're trying to down convert. And the green here is just either noise or an interfering signal from some other location that doesn't contain anything we want. We don't want it at all, but it happens to be present in our system. So what happens when we multiply this LO signal by the green and the blue, S1 and S2? Well, if you look at the output, you'll have the sum and difference frequency. So you have F image minus FLO as well as F image plus FLO. And then you'll have FLO minus FRF and FLO plus FRF. And you use absolute values where needed because you don't want a negative frequency. So what happens is that if this F image minus FLO in absolute value is equal to FLO minus FRF in absolute value, then the output will end up in the same place. And that's a problem because if you have 2 signals that are right on top of each other in frequency, it's virtually impossible to filter out one from the other. And so this IF filter here is showing the bandpass filter you'd have on the output of the mixer in order to get rid of any other signals. And what will happen is that that green guy will pass right through it, and in the output you'll have both. And that's not what you want. That'll degrade your signal of interest. So how do we solve this problem? Well, we got to get rid of this F image before the mixer. And to do that, we use another filter that's basically bandpass filters the FRF, which gets rid of the F image before mixing. So that's another application of a filter. Now another one is on the receiver, just after the antenna. The antenna is going to be receiving anything that's being sent out in the electromagnetic spectrum, some more so than others, depending on the antenna geometry. But what you need to do is filter out just your signal, your frequency band of interest, and get rid of all the other interference, similar to this image rejection filter. And to do that, you just use another bandpass filter. And so another application is, for example, on the output of an oscillator, if you want a very clean sine wave, you can bandpass filter out all of the harmonics of the fundamental frequency, and that'll get you a much cleaner sine wave. And I say here the list goes on because it does. Filters will pop up over and over again in RF systems. Right, any questions? No, okay. So what type of filters do we have? I'm sure many of you have seen this before, but let me just go over it one more time. So at the top here, we have a low pass filter on the left, and on the right, we have a high pass filter. And I'm sure you all know what to do. Low pass filter passes low frequencies, high pass filter passes high frequencies. Well, that's all fine enough. Then we have a band pass filter, as well as a band stop filter, also called a notch filter. And further down, we have another type of notch filter. And you can kind of see the difference between them. One passes low frequencies better, that's this guy, and one passes high frequencies better, and that's that guy. And then lastly, we have an all-pass filter, which passes all frequencies exactly the same in magnitude. And you might ask, what's the point of an all-pass filter? And the answer is that the phase response is what's important. So here is I'm only showing the magnitude response of the filter. If we look at phase, you might have something that looks like, if I plotted phase on this axis, for example, where here is 0 degrees and here's 180 degrees. Phase might look something like this. And that could be useful for many different things. For example, like phased array antenna, for example. But I won't go into that here. So for this project, we're mainly interested in low-pass filters, bandpass filters, and potentially high-pass filters, but probably not. So I think one important thing to note here is next to each of these responses is a little diagram. And these are basically plotting the poles and zeros of the filter response. So for the low-pass filter, in this case, it's a second-order low-pass filter. There's 2 poles. And what that means is a pole essentially props up the filter response, the frequency response. So if you're looking along the j omega axis, which is basically frequency, at DC, 0 frequency, right here, we're right in between the 2 poles, and those poles are going to prop up the frequency response, allowing signal to pass, which is what's indicated in the filter response right here. So when we're at DC, we're passing signal. And then as we move up in frequency this direction, at some point we start moving away from both of the poles. And at that point, there's no longer any poles propping up the frequency response. And that's when this curve starts moving down. And then as we go to infinite frequency, eventually it goes to 0. And you see the opposite thing with the high pass filter, and that's because now there's a 0 at 0 frequency. So at DC, the response is 0. And as we go higher and higher in frequency, we're moving away from that 0, and that allows the frequency response to go up. And so on. So hopefully that makes sense. All right, so now we get to the RC filter and why we don't use it. So I have here just a single first order RC low pass filter. So the series resistance is 50 ohms. The capacitance is 3.18 nanofarads. And if you go through the math, 50 times 3.18 nanofarads times 2 pi, take the reciprocal, you get 1 megahertz. So the 3 dB bandwidth of this low-pass filter is 1 megahertz. And so I plotted the frequency response of this thing right here. And sure enough, at 1 megahertz, which is right here, the we're 3 dB down from 0 dB. So that's the bandwidth of this filter. All right, so remember what we've been doing is we've always had a source resistance in series with our, our voltage source. Because at RF frequencies, it's very difficult to get our source resistance close to 0. That might be easy at like DC or low frequencies, but at RF frequencies, you're not going to do it. So what we can do is we can use that source resistance as part of the filter itself, and that's kind of what I did here. So if I assume this entire block here is part of the source, and then this capacitor is just the filter, then we get the response as shown and everything's hunky-dory. However, we also have a load that we're always trying to send a signal to. And we have the same problem where we can't have a load with a very high input or very high resistance. And that's because there's always some parasitic or something that's going to lower the resistance for us. For example, with an amplifier, there's always some capacitance at the base of a transistor, and that's going to lower the input impedance. So you always have to take into account some resistance or impedance at the output of the filter, which is going to change the filter response. It's essentially loading the filter. All right, so let's do that. So I have the same source here, with the 50 ohm source resistance. I added a 50 ohm source resistor. And if you go through the math, you'll find out that the 3 dB point of this filter is now 1/2 pi times R1 in parallel with R2 times C. So, well, I might have done that wrong. No, I did that right. So what I did is 50 in parallel with 50 is 25. So I've essentially divided the resistance by 2. So I have to multiply the capacitance by 2 to get the same 3 dB bandwidth. So that's what I did. I increased the 3.18 nanofarads to 6.36 nanofarads. And now if you look at this graph, right here is 1 megahertz, and we're back at 3 dB below the maximum. And you'll notice that our maximum is no longer 0 dB. Now it's -6, or roughly -6. And does anyone know why? Someone?
Is it because of the voltage divider, R1 and R2?
Right, exactly. So if you imagine, take a look at DC, for example, 0 frequency. You can ignore this capacitor because it's open circuit. So we get a 50 ohms in series with another 50 ohms, and that just gives you a voltage division by 2. And remember that the 2 in dB scale, you do 20 log 10 of 2, and that comes out to roughly 6. So that's why we're at -6 dB at low frequencies.
Can you explain real quick one more time where the R1 in parallel with R2 in the calculation comes from?
Yeah, so if you, this filter, you can calculate the response just by doing a voltage division. So it's a voltage division. If I call these two guys Z, then V out over V in is just equal to Z over R1 plus Z, right? And if you do the math and calculate when this function drops by 3 dB, you'll find it'll come out to this value right here.
Okay.
Yeah, All right, so the 6 dB here is to be expected. So regardless of what type of filter we use, we're always going to get a 6 dB loss from input to output because we have that voltage division. So that's nothing to worry about. When you typically look at filter responses, though, you usually ignore the source resistance, and you only look, or I'm getting ahead of myself. So, but usually you kind of shift this curve up to 0 dB, and you kind of ignore whatever voltage division you're seeing. All right, so but what's the problem with this, though? Because it seems to work just fine. And it does work fine if all you need is the filter to roll off by 20 dB per decade, because the slope of this guy is just minus 20 dB per decade frequency. And if you haven't taken 110 or 141 or the equivalent, you might have not heard about this. But if you have a single pole in your transfer function, then as frequency increases, it's going to roll off by 20 dB per decade. That's just a well-known result. All right, so if that's all you need, that's fine. So like if I want to reject something at like, I don't know, 100 megahertz, which is 1 times 10 to the 8th, which is this guy right here. And this would work fine because right now this filter is at like minus 45 dB. You got to add 6 to that. So it's really like minus 39 dB below the passband, which is this guy right here. Here's the passband. But oftentimes frequencies are much closer together, and you have to essentially increase this roll-off rate such that you get more rejection at lower frequencies. So like, let's say I have some signal at 2 megahertz, which is right here. This is 2 megahertz. And if I look at how much rejection we get, this is at what, like minus 14 or so. So that's only 8 dB below the passband, which is not much. Usually, I mean, it depends on the exact application, but 20 dB is nice. 40 dB is even nicer. So clearly, you need to do something more in order to get higher rejection at lower frequencies. And you might think, let's just cascade more of these RC filters. The problem is that due to the fact of having resistors in your filter, you're just going to incur more and more loss at your passband frequencies. And that's really undesirable because usually signal is a precious commodity. And if you're degrading your signal, you're going to have a bad time. Any questions on that? Okay. So I don't know how many of you have seen active filters. And this is kind of one way to cascade RC filters is by sticking a buffer op-amp between them. So like if I have a RC filter like this, and then we'll have a op-amp acting as a buffer, and then I have another RC filter. This will mitigate the loading effect of cascading RC filters. However, there's a significant problem with this, and the problem is this op-amp. And the problem with op-amps is that they don't work at our frequencies or microwave frequencies. Or you have to pay a real premium to get them to work at those frequencies. And that's the same problem with active filters. So active filters basically implement LC filters that I'll talk about without the inductor and instead use an op-amp. And the problem with op-amps is that they don't work well at high frequencies. Okay. So now we get to the LC filter. which is really what we're going to be using. So here's a very simple second order LC filter that I made. We have our source resistor, 50 ohms. We have our load resistor, another 50 ohms. And here we have a capacitor and an inductor. So the main difference between RC filters and LC filters is the presence of this inductor and the lack of any resistors, except for the source and load resistors. And because we're only using reactive components in the filter, there is ideally zero loss in the filter because reactive components can't dissipate power. All right, so if you look at the filter response, you'll notice something slightly different. We're still at minus 6 dB here, which is to be expected at low frequencies. However, the roll-off of this filter is no longer minus 20, now it's minus 40 dB per decade. So before, we remember when we had at 2 megahertz, which is right here, we had only 8 dB of rejection. Now we're looking at, this is like minus 18 or so. So now we're looking at an additional 4 dB, which is not much. So now we're looking at like 12 dB total of rejection. But if we go down further to like 100 megahertz, before this was at minus 45, now we're at minus 80, 85 or so. So that's an additional 40 dB of rejection, which is pretty good. And all we did was added an inductor. So why is it able to do that? Well, that's because this is a second order filter. There's 2 poles in the frequency response due to the 2 reactive elements. And that allows this transfer function to drop off, or I should say frequency response, to drop off by 40 dB per decade instead of 20 dB per decade. So what does the addition of the inductor really do? It adds a complex conjugate pull to the transfer function. And if we cascade these L's and C's together, we can create a higher order transfer function that can have an even steeper drop. And there's some other nifty things we can do, which we'll see shortly. But the main thing about LC filters is that they take into account the load resistance in the design of the filter. So unlike the RC filter, which doesn't really take into account the load resistance, and you kind of finagle it to work correctly if you add the load resistance, with LC filters, the design assumes you have some resistance that's loading it down. All right, so there's 4 main types, or I should say 3 main types, and one has 2 different variations of LC filters. And there's some additional ones, but they're kind of more esoteric and not used as often. But so the main one is the Butterworth filter. And this is probably the one that's most relatable, I should say, and most similar to the RC filter response. And it kind of looks like an RC filter. So in the passband, it looks pretty flat, and then there's a roll-off and as you go to the stop band. But the key characteristic of a Butterworth filter is that there's no ripple anywhere. It monotonically decreases as frequency increases. And you can see that's definitely not the case with the other ones. The problem with it, though, is that it has the slowest ripple, the slowest roll-off of these filters for a given filter order. We have a comment. What does the order mean? Right, so the order of a filter is basically the number of poles in the filter. And the number of poles is usually equal to the number of inductors plus the number of capacitors. So in the case of this second order Butterworth filter here, there's 1 capacitor, 1 inductor, so it's second order, and that means it has 2 poles. So hopefully that answers your question, Cody. Okay. So any questions about the Butterworth filter? Okay. All right, so on to the Chebyshev filter. So you can see that there's something pretty different between these two. And that is the fact that the Chebyshev filter has some ripple in either the passband for type 1 or the stopband for type 2. And when people say Chebyshev filter, they're almost always referring to the type 1 variant, because the type 2 is pretty, it's much more rare to see it. So this ripple in the passband may or may not matter to you depending on the application. But what it allows the filter to do is roll off much more sharply than the Butterworth filter for a given filter order. And so the difference between type 1 and type 2 is that in type 1, the ripple's in the passband. In type 2, the ripple's in the stopband. Where there's not ripple, it's monotonically decreasing. All right. Now we go to the elliptic filter, which is very interesting, actually. So it has ripple in both the passband and the stopband, but it has the sharpest roll-off of all of these filters for a given filter order. And sometimes that might be very desirable. For example, if you have two frequencies that are really close together and you need, the sharpest filter possible, maybe the elliptic filter is the one you want. The problem with it, though, is that, or one of the problems, is that elliptic filters tend to be more difficult to design, and they tend to be more sensitive to component variations. So with all of these filters, if your capacitor varies by like 5%, that could screw up the entire filter response, and you'd have to tune it to like kind of exactly the right value to get the filter response to look right. So that's all nice and good. Let me talk a little bit about the theory before we get into the implementation. So first, for the Butterworth filter, I got this nice visual stolen from Wikipedia, and it shows the filter response for different orders of the filter. So you can see for a first order filter, it drops off by 20 dB per decade. You can kind of see that at 10, it's at -20, at 100, it's at -40 at these 2 points. So that's 20 dB per decade. And then second order drops off by 40 dB per decade, and so on. You get 60, 80, and then 90 dB per decade. And as you keep increasing the filter order, it'll get sharper and sharper. Okay. So the way the Butterworth filter is kind of designed is that the transfer function is defined like this, where you have 1 over 1 plus j omega, omega is just frequency, over j omega c. Omega c is the cutoff frequency, so the 3 dB point, to the power of 2n. So that's the magnitude squared of the frequency response. And if you kind of look at this and you solve for the poles, so you set this equal to 0, the denominator, to find the poles, and you'll basically get omega over omega c to the power of 2n is equal to -1, which is equal to e to the minus j, I think. Well, plus j times pi, actually. There we go. And now if you raise both sides to the power of 1 over 2n, you get omega over omega c is equal to e to the j pi over 2n. Okay. So what this is showing is that if you assume omega c is 1, just to kind of normalize everything, the poles of the Butterworth filter are basically all roots of unity. So, you take one, the complex 1, and you raise it to the power of pi over 2n, and you get all the poles. Okay. And then if you do some math, and I'm not saying the math is easy, but you can show that if you the derivatives of this transfer function magnitude squared all the way up to the 2nth derivative are equal to 0 at 0 frequency. And so what that means is that by making the derivatives equal to 0, you're making that function as flat as possible in the passband. And so that's why the Butterworth filter is also called the maximally flat filter, assuming you have a 0 ripple, because you can get flatter filters if you allow ripple in the stop band, but don't worry about that too much. So if you need a really constant passband, you use a Butterworth filter. That's basically it. And of course, I have the Wikipedia page there for you if you want more information. So onto the Chebyshev filter. The Chebyshev filter is based on Chebyshev polynomials, which is some Russian guy. And what it does is it maps the nth order Chebyshev polynomial to the poles of the transfer function. So this top graph here is showing a few Chebyshev polynomials. What the Chebyshev polynomials are is basically a series of functions that follow a particular trend. I forget. I don't know how they're mathematically defined, but there is a definition for them. And this is showing order 0 up to order 4. You can kind of see how they're polynomials. So for order 0, you just have a constant 1. That's the top line there. Then for first order polynomial, you have a line. Second order polynomial in green, you have a parabola, and so on. So the way the filter itself is defined is through this equation. This is giving you the poles of the transfer function. And here epsilon is called the ripple factor. That defines how big this ripple here is. And this is assuming that the cutoff frequency is 1, by the way. So it's normalized. You can always scale up this to higher frequencies if you need to. And in this equation, the t is the Chebyshev polynomial. So anyways, that's how it's defined. And here again is the Wikipedia page if you want to learn more. But an important thing to note here about this filter is that it's also called the equiripple filter. And you can kind of see that where each of these polynomials are bounded between 1 and -1. And when that's scaled to the filter, that'll bound your ripple to something between 0 dB and something else. And that something else is defined by this ripple factor. And that's up to the designer to choose. Okay, so how do we actually implement these filters? Well, the most common way is called a ladder filter, also known as the Cauer topology. And what you do is you have a series reactive element, you have a shunt reactive element, followed by another series reactive element, a shunt reactive element, and so on, for however many you need to create your filter. So for a second order filter, I just have these two. And then for a fourth order filter, I have these. And for a third order filter, I have these 3. And so this is for a low pass filter, and you can guess it's a low pass filter because there's a series inductor and shunt capacitor. So at high frequencies, the inductor is going to block you and the capacitor is going to short out your signal. And at low frequencies, you go right through the inductor and the capacitor is open circuit. So this is a low pass filter. For a high pass filter, you just replace the inductor with a capacitor and the capacitor with an inductor. So you get something that looks like this. And so on. And then for a bandpass filter, I wrote it here, you'd have a series LC. Let me get rid of this. Any questions, by the way, while I draw this? No? Okay. It's a humongous capacitor, but go with it. So this would be a bandpass filter, specifically a fourth order bandpass filter. And to create a band stop filter, you just swap the series LC with the parallel LC. And you can kind of see how that works. So at resonant frequency, for example, let's say this is L, and this is C, and at 1 over omega LC, a square root of omega LC, 1 over square root LC, where this is omega. Can somebody tell me what the impedance of this is, the series LC? So when these two are resonating with each other at that frequency, what's the impedance? You basically got two choices. It's either infinite or zero. Which one is it? Someone guess.
0.
Yes, thank you. And that makes sense because this is a bandpass filter. So assuming that we want to pass this particular frequency, we should expect this to be 0 ohms at that frequency. And then this guy, what would this be? At resonance?
Infinity.
Yes. So always remember that parallel LC goes to infinity and series LC goes to 0. That's very important. And that'll tell you how to construct these filters as well. So for a band stop, we just replace the series LC with the parallel LC and the shunt parallel LC with the series LC. I said that this is L and this is C, and they resonate at the resonant frequency of the bandpass filter. But that's not quite true when you're designing bandpass filters. So what you actually do is you vary the resonant frequencies of these series and parallel LCs in order to widen the bandwidth of your bandpass filter. So like if you move one to the lower frequency and one a little higher in frequency, and you look at the overall response of the filter, you'll find that the bandpass characteristic will have a wider bandwidth. But anyway, so let's design some filters. So it's possible to design it by hand, where you write out this ladder, the LC ladder, you find the transfer function, and you solve for the poles, and then you set the poles exactly what they need to be based on whether you're choosing a Butterworth filter or a Chebyshev filter or so on. You can do that. That's just very tedious. So thankfully there exist softwares that find the values for you, and it's not very instructive to compute the values because you end up doing like, I don't know, bizarre hyperbolic inverse cosines and other things. So let me show you how this is done here. There's online calculators, so that's one I'll use. And the one I found most helpful is this guy here from rftools.com. They have a bunch of other calculators, but we'll be using the filter calculator. And when you load up the website for the first time, you get this pretty little picture and this humongous filter. So let's make a little smaller filter. Let me go to a low pass filter. I'll use a Butterworth filter. And I'll make it a third order filter. And I'll make the cutoff frequency 1 megahertz. And notice you can also put the input and output impedance. Those are pretty important. So I'll press compute, and it'll give me a nice little filter of a third order Butterworth filter. You usually want to stick to odd ordered filters, because that makes your filter symmetric, and that's a desirable property usually. So I'd stick to odd order filters. Anyway, so here it plots the frequency response for you, and that's nice of it. And you'll see an S21 and an S11. And if you've never taken 163A, I believe, or yeah, 163A, that's microwave circuits, you'll have no idea what S21 and S11 are. Well, they're called scattering parameters, but that's not so important. The S21 is it's also called insertion loss. And what you can think of it is as like the V out over V in of this filter, in dB scale, of course. Except V in is the voltage right after the 50 ohm source resistance, and V out is the voltage across the load resistance. So before, when we had that minus 6 dB at low frequencies, that's because we were taking the input voltage to be right here before the source resistance. But here, if we take it after, then we get 0 dB at low frequencies, which makes sense. So let's make sure this graph here makes sense. So at 1 megahertz, we should expect somewhere around 3 dB, which it is, minus 3 dB. And if we go to like 10 megahertz, or 20 megahertz, I mean, it's at minus 18, which, if you recall from the lecture, when I had the same exact filter, that's what it was. It was minus 18 below the peak, or 0 dB. Actually, no, it wasn't, because I was using a different type of filter there, second order filter. But if you were to simulate this, that's what you get. So we can do that pretty easily. If I pull up LT Spice here, and I bring in a voltage source, a resistor, a capacitor, another capacitor, and an inductor, and I connect everything up. Okay, and I'll use the AC analysis. So I'll set the AC amplitude to 1. I'll set our source resistance at 50. I'll create a load resistor of 50. And then I'll punch in the values for the capacitors, 3.183 nanofarads. And then the inductor is 15.92 microhenries, which you may remember is a little on the high side. So I'll go into the simulation configuration. I'll set an AC analysis. Let's go decade. I'll start at 100 kilohertz. I'll go to 100 megahertz. Oops, this should be here. And I'll have, 100 points per decade. So if I simulate this, and I go here, I screwed up because I forgot the ground. Okay, one more time. There we go. Okay, so and let me also label the in right here and the out right here. So now I'll simulate this again. I'll add a, I'll click this guy and then I'll just modify this to be V out over V in. Okay, so now it's at 0 dB at low frequencies and then it increases at higher frequencies. And if I add a cursor to, where's the thing? Here it is, to 2 megahertz, which is right about there, you see it's minus 18 dB, which indeed matches this guy at minus 18 dB. Okay, so that's fine. What else can we do with this calculator? Well, we can use a Chebyshev filter. And notice there's an additional option. There's the passband ripple. So that's an important parameter. A higher ripple will give you what it sounds like, more ripple in the passband, but it'll also give you a higher roll-off rate in the stop band. So if I set this to like 0.5 dB and I press OK, it's hard to see, but at 20 megahertz, now we're at 19 dB instead of 18. So it's not much of an improvement. But if you were to go higher in frequency, you'd notice a bigger change. And another important thing with Chebyshev filters, the cutoff frequency is always defined at the passband ripple level, not 3 dB. So if I go to 1 megahertz here, you'll see it's at roughly 0.5 dB or so. It says 0.6. But this graph thing is pretty terrible. So it's roughly 0.5 dB or minus 0.5. And that's because I set the ripple level to 0.5, and that's what it'll call the cutoff frequency at. Okay, and then I can always increase the order. So let's say 5th order Chebyshev filter, and you'll notice that it becomes even steeper. Well, that's nice. And if I make the ripple smaller to say, you'll see the ripple there. It's kind of hard to see. But if I set it to 0.1, then the ripple is even smaller, but it comes at a cost of less roll-off in the stop band. Okay, now on to bandpass filters, which is the main one we'll be using in this project, I think. It gives us more options. So I'm still on Chebyshev, so I still have the passband ripple. Now I have a lower cutoff frequency and an upper cutoff frequency. So a bandpass filter always has some bandwidth, and you need to define that bandwidth. Okay, so for our mixer, for an example, let's say I choose the lower cutoff frequency. We want to pass 27 megahertz, so I'll set the lower cutoff frequency to be 26 megahertz, and the upper to be 28. So anything between these will be in the passband, and anything outside of these will be in the stop band. And I compute, and I get a beautiful bandpass filter. And this you can put this on the output of the mixer, and it'll filter out anything outside of the passband. However, for our mixer, remember that we have the 28 megahertz LO leakage. And where is 28 megahertz? That's right here. And you'll notice that it's not really doing anything at 28 megahertz. It says minus 0.7 dB or so. And that's not attenuating it at all, really. You want more like minus 20, which is down here. So part of your assignment will be playing with these cutoff frequencies and the filter order in order to be able to reject the 28 megahertz. I should also mention the topology. So let me go back to the low pass filter. Let's press compute. So we're back at the 1 megahertz low pass filter. You have two options here. You have shunt first and series first. And that's because there's multiple ways to design this filter topology. You can have the shunt capacitor first, or you could have the series inductor first. So right now I have it set it to shunt first. It'll give me the capacitor first. If I set it to series first, it'll give me the inductor first. So one will have 3 inductors and 2 capacitors. One will have 3 capacitors and 2 inductors. And depending on which component values and what components you have at hand, one may be more reasonable than the other. And if you're sneaky, with a bandpass filter, for example, if I go to here, shunt first, or series first, for example, you'll notice that there's a series capacitor and a bandpass filter. And that could allow you, if you had this on something like the output of an amplifier or an input of an amplifier, that could allow you to get rid of the coupling capacitor that you usually have there, like the one that separates DC from AC. So you could actually use a filter to separate DC and AC. So that's just a little technique to use. Anyway, for bandpass filters, this calculator gives you a lot more options. You could do conventional first, which is what I showed you earlier in the slides. So you have shunt first or series first, same thing as low-pass filters. So I'll just change which one comes first. There's also what it calls direct coupled. And what these do is use something called a impedance inverter, which is something I won't talk about, but it allows you to use different topologies. So for example, this guy has no series inductors, it only has shunt inductors. But you'll notice that you have to use, it changes the component values a little. So there's trade-offs you have to make. And sometimes it might mess up your filter response. Then there's also totally tubular over here. Never actually tried this one. That's kind of interesting. So yeah, as you can see, there's many different ways to construct these filters. And then for high pass and band stop filters, same exact thing. It's just kind of reversed. So like if I go to a band stop filter, instead of having a pass band at 27 megahertz, now I'll have a big notch there. So 27 megahertz ain't getting through this guy. And here you'll see what I talked about, where instead of having a shunt parallel LC, now you have a series LC and a series parallel LC here. So any questions about that?
Can you repeat one more time why the order should be an odd value?
Yeah, so with Chebyshev filters specifically, let me go to a low pass filter here. In the third order, so let me compute that. Notice how it's symmetric. So if I move this voltage source to the other side and apply the voltage here instead, I would get the exact same response at the other side.
Right, yeah.
So that's a nice property. If I make this a second order filter, it kind of looks like that, which is pretty terrible, right? So basically, even order Chebyshev filters don't work very well. And if you kind of look at the, where is it? Here. So even order polynomials are different from odd order polynomials, and that kind of contributes to how the filter response will look like. I don't really have a good mathematical explanation for you, but if you do go through the math, you'll find that you have to do something extra in the filter design to take into account the asymmetry of the filter.
Okay.
But if I go to a Butterworth filter, second order filters work a little better. So you can see it rolls off better now. If I go to a fourth order, it'll work as well. But usually you want to stick to, at least with Chebyshev filters, you always want to stick to odd order filters. So that this one looks okay. But I forget exactly what you have to do, but there's some additional calculation this thing does in order to get it to work right. So sorry, I don't have a great answer to your question.
That's okay. Yeah, I got it.
Yeah, anything else? Otherwise, we'll move on here. Okay. Like that. Okay. So hopefully all of that filter stuff made some sense. So with that, we'll have our next assignment on due next week, Friday. I don't think it'll take that long because the filter design itself is kind of straightforward since you're using a calculator. And what you'll be doing is you'll design some filters, first of all. One will be the filter you place directly after the antenna, so that'll filter out any adjacent frequencies that are interfering with the frequency of interest, which is 27 megahertz. And then for the up converters and down converters, you'll need a filter on the output to get rid of the sum and or difference frequency, and plus all the harmonics that are in the output. So for the up converter, you'll need a 27 megahertz bandpass filter. That's what we talked about. For the down converter, you're going from 27 megahertz to a lower frequency. And I wrote here 0.5-ish, 0.5 megahertz-ish, because I don't have an exact number for you right now. And that's kind of a design choice, what exactly you want that frequency to be. And so you'll need a bandpass filter for that guy as well. And I wrote here, you got to take into account which frequencies you need to block. And I said that with the up converter, the most important thing is getting rid of that LO from the LO leakage. So because you have the 27 megahertz right next to the 28 megahertz, you have to make that bandpass filter rather narrow. And that's not easy. And then lastly is to ensure all component values are reasonable, because if you just go blindly with this this filter calculator here, you'll get sometimes you might get some wacko values. So if I go to bandpass here, I compute this, you'll notice like you'll have 6 picofarads. That's kind of on the low side. It's doable, but it's kind of on the low side. If I make this even more narrow, so if I go to like 26.9 and then make this 27.1, now you're at 608 femtofarads. And it's kind of cute looking how narrow this is. But 608 femtofarads is something you're not going to be able to create in this type of circuit. It's possible in integrated circuits and what are called mimics. Mimics are monolithic microwave integrated circuits. But you kind of need either special parts for that or special fabrication techniques. So that's that. And here you have a 57 microhenry inductor. And there's no way you're going to get a high Q 57 microhenry inductor at 27 megahertz. They just don't make them. So yeah, that's something to keep in mind. You can't go arbitrarily narrow in bandwidth here. Okay, what else do we have? Here, with your up converter expertise, you'll also be designing a down converter, which is what you're going to stick the down converter filter after. So you're going to do the same thing you did with the up converter, except converting 27 megahertz to 0.5 megahertz-ish for that part of the assignment. All right, so last thing I'll mention is when you're designing these filters, you usually want to keep them to a maximum of 5th order. If you start going to like 7th order filters or 9, what'll happen is that if you, like due to component tolerances, if one of the values is slightly off, it'll screw everything up and your filter won't work very well. So yeah, anyone have any questions? Otherwise, we'll call it a day. Anyone going once, going twice? All right, that's the show.